Okay, thanks for coming and listening. Today I'm going to give a little talk that I sort of call measurements and models, or measurements to models. Our Earth is a really complex planet. Processes are occurring on the ocean, in the atmosphere, on the land. And to understand our planet, we really need to not only understand the individual processes, but the connections between the processes. This is the so-called NASA blue marble. It's round, it shows continents, but it is not an instantaneous image of the hemisphere of the Earth. It's actually assembled from low Earth orbit imaging spectrometers. Next, please. However, from the Lagrange 1 point, 1.5 million kilometers away from Earth, on the Earth-Sun line, we are acquiring measurements with an imaging spectrometer called EPIC of the entire sunlit hemisphere of the Earth with high spatial resolution and in about 10 different bands. And of course, if you're 1.5 million kilometers away from Earth, you're outside the moon's orbit. So on occasion, the moon cuts through, as in this transit from Discover Epic. And what we're seeing of the moon there is the dark side of the moon, the side that we can't see from Earth, the side that faces the sun, the dark side of the moon. You figure that one out. Next, please. However, closer to our planet, orbiting at altitudes of a few hundred to 700 or so kilometers, or 800 kilometers, we are making measurements from the vantage point of space of many different quantities, all at the same time, with uniform accuracy, global coverage, high spatial resolution, and relatively high temporal frequency. This is an animation of just our NASA research satellites. But of course, to answer questions about the evolution of our environment, we need to make measurements, or we need to use measurements of from many other satellites as well. And here we're going out to L1. But from the collection of low Earth orbiting satellites, we are learning many things about our planet. Next, please. If we take measurements of one quantity, greenness, chlorophyll on the Earth for long periods of time, and global coverage and relatively frequent measurements, we can not only detect short period variations everywhere, but we can start to see seasonal and trend variations. I love this 20-year animation of the Earth's biosphere. Phytoplankton in the ocean, chlorophyll, and land cover on land. You can see so many different things on so many different time scales. You can watch seasonally as the Sahel region between the Sahara and the savanna and the jungles moves north and south with the sun. You can see the greening up of the northern hemisphere during boreal summer, and you can see greening up of the southern hemisphere during austral summer. You can see the impacts of rain on the continents leading to flooding through the Amazon, nutrient-rich waters put into the western tropical Atlantic, causing phytoplankton blooms. You can see the impacts of winds blowing off the continent and through the three gaps in Central America, Panama, Papagayo, and Tehuantepec, causing turbulence in the ocean on the downwind end of the gaps, and again, mixing nutrient-rich deep waters up into the euphotic zone and causing phytoplankton blooms. There's so much here I could talk for the entire rest of the time, but I won't. Next, please. There's other kinds of life on Earth, and by making measurements with extremely high sensitivity under low light, that is dark conditions, we can actually see that this planet for some reason, emits light from the continents and occasionally from the oceans. This is sort of the higher part of the biosphere, the sentient part. Maybe these are night lights, and you could teach an entire sociology course from the distribution of humans on this planet. And I won't go into all kinds of things there, but I'll point out a few things. This is not an island. This is South Korea. Plenty of lights. This is North Korea. Not very many lights at all. And more. Next, please. So that was life on Earth and lights. We can also use our satellites over long periods of time, even if they're not measuring every single occurrence of a particular phenomenon, to build up statistical climatologies. And over a long period of almost 17 years or so, the Tropical Rainfall Measurement Mission measured lightning over the Earth. Lightning strikes many times per second globally. We only measure it where the satellite is. But over periods of time, one can actually build up from individual measurements climatologies showing where the lightning occurs and where it doesn't. Over land, over ocean. This is the first lightning global climatology with uniform statistics ever derived. Next, please, from Trim. We can make measurements of atmospheric phenomena, some of which are quite ephemeral. These are measurements of a particular pass of Hurricane Irma this past September from the GPM, Global Precipitation Measurement Core Observatory. We are not only measuring with high spatial resolution and good coverage the total rainfall, but as you can see, we are also making measurements of the vertical distributions of raindrops and other quantities, lending insight into the sub-processes underlying precipitation. Next, please. But since it rains a lot, but very ephemerally over the globe, making measurements from a single satellite is not good enough for measuring precipitation over the globe. But many different low Earth orbiting satellites have instruments on board that are related to or can be interpreted in terms of Earth, in terms of precipitation over the Earth. Sorry if you got seasick on that one. By taking all of these measurements and combining them for the very first time, we actually understand quantitatively precipitation over our globe with spatial resolutions on the order of 10 kilometers, temporal estimates on the order of 30 minutes or so. I like to say that before the Global Precipitation Measurement constellation came into being, the only thing that we knew about precipitation really quantitatively was wherever I was going to go on vacation was going to rain there then. Next, please. By taking the satellite measurements and understanding something about the processes, we can use the measurements to drive models. And it's sort of easy. I'm an oceanographer. It's relatively easy, relatively, to drive ocean models because the ocean evolves relatively slowly compared with the atmosphere. This is one of the most up-to-date ocean models right now, one of the most advanced from a dynamical standpoint, and you can see that the ocean is a turbulent fluid, okay? We really didn't know that before the advent of the high-resolution models and the satellite measurements. Sure, you can see things like equatorial currents if you more or less squint, or the Gulf Stream, or the Kuroshio, the western boundary currents, but in fact, the dominant feature of oceanic circulation is the mesoscale eddies in the ocean, just as they are, by the way, in, say, Jupiter's atmosphere. Next, please. But it's a much more difficult problem to make sufficient measurements and to have enough dynamics in models in order to predict atmospheric evolution, that is, the weather, because the atmospheric spatial scales, while larger than the ocean, the spectrum is much richer than the ocean, and the atmospheric temporal scales are much smaller. In order to do accurate predictions of atmospheric motions and dynamics, we really need to assimilate measurements from many different satellites, from many different measurement systems, and measurements of many different quantities. Not just things like sea surface temperature or sea surface height, but vertical profile measurements and many others. And you can see here in an assimilation cycle, the buildup of measurements from different satellites that are going by, from aircraft that are taking measurements, etc. The assimilation and modeling problem is complex. Next, please. When we have good dynamical measurements of the atmosphere, and we also make measurements from space of long-lived atmospheric composition quantities like, say, carbon dioxide, which has key radiative impact on the Earth, we can start to couple inside our models the measurements of composition and the dynamics. What's shown here is 1 year of carbon dioxide measurements and model predictions from a global general circulation model, and you can see how the carbon dioxide in the atmosphere over the year varies regionally, varies seasonally, varies on short time scales, and even varies vertically. We can use the models to assimilate different measurement types. Next, please. Similarly, we can measure and then assimilate into models things like aerosols generated by people anthropogenically from fires, aerosols generated from winds over arid desert areas, aerosols generated by winds over the ocean, bringing salt particles into the atmosphere. We can see with the models how the atmospheric dynamics cause transport of those aerosols. This is shown horizontally. We also have it vertically from the models, and with lasers on satellites, LIDARs, we can measure the vertical distribution of aerosols as well. So this is sort of aerosols and large-scale atmospheric dynamics with the emphasis on the different kinds of aerosols. Next, please. This is the latest hurricane season with just a couple of aerosols, carbon aerosols and dust aerosols and sea salt. And this is going to take a little bit too long based on the amount of time that I have left. But what you can see are detailed interactions between the atmospheric dynamics and the atmospheric composition, the aerosols. You can see as the various hurricanes spin up, and if we could run this long enough, you could see how especially dust coming off the western portion of the African continent interacts with developing and evolving hurricanes. And towards the end of this, you actually see a Hurricane Ophelia start in the eastern Atlantic, move all the way up, getting a lot of dust from Africa and some fire dust, fire particulates, aerosols from Portugal and Spain, and taking them all the way up to the British Isles. Next, please. I think this is my last one. So, from the vantage point of space, we're understanding our planet. We're making measurements of many different quantities. We're using our understanding and codifying it in terms of processes in the models. We're taking other measurements and using them to initialize and assimilating them into models, and we are able to predict in its, almost in its full glory, the many different quantities and the many different processes that are taking place on Earth. Only from the vantage point of space is this possible. Only from research programs like we have at NASA that ask questions about Earth systems as opposed to individual missions can we come to this understanding. Thank you very much.